Now we're moving on to the coding part of this problem, where we're actually going to define a situation in which we have real numbers, and then we're going to solve that using the differential equations we found from the last part. And I went ahead and did the liberty of importing all the packages that we're going to need for this problem, but we can go ahead and go over those anyway. So starting off with import np as np, that's just getting numerical Python so we can use it for packages. And then we're going to be making subplots. So from plotly subplots, we're going to import make subplots because we're going to end up graphing these. And then these next two lines basically just change the background to dark on the plots that we're making because I think they look better. And then from we're also going to be solving with these differential equations initial value problems as well as root problems. So from the ngrate package in SciPy, we're going to import the solve IVP function. And then from the optimize package, we're going to catalog, we're going to import the root function. So the next thing we have here is just a small function that is using the Anton equation, so that any partial pressure of water that you put in at a given temperature, that water is going to return us with the saturated pressure at that temperature. So basically any temperature that we put in, it'll automatically find us the saturation pressure of the water at that given temperature using this. And then this is just the Anton equation for water. Okay, so let's go over the what was given to us in this problem, as well as a couple things that we need to add. So starting with the heat transfer coefficient, we know that our heat transfer coefficient in this problem is going to be 10, and that's in watts per meter squared Kelvin. And then we have the universal gas constant R. In this case, we're using the 8.314 version, which is going to be in joules per mole Kelvin. And then moving on to the density of the air, which I'm calling rho air, is going to be 1.2, and that's going to be kilograms per cubic meter. And then moving on to the specific the heat capacity of the air, which is 1,000 joules per kilogram Kelvin. And then we also need to know the heat capacity of the water as a gas and as a liquid. As a gas, it's 2,000, again, joules per kilogram Kelvin. And then as a liquid, water has the heat capacity of 4,190 joules per kilogram Kelvin. Moving on to the heat of vaporization, it's 40,700 joules per mole. And then using the Lewis relation, we know that the mass transfer coefficient Kc is equal to the heat transfer coefficient over the volumetric heat capacity, which in this case would be the density of the air times the heat capacity of the air. Our specific area is going to be 5, and then that's meters squared per meter cubed. And then we have the molecular weight of water, which is going to be 18 times 10 to the negative third, which is going to be kilograms per mole, not grams per mole. And then molecular weight of air, which is 29 times 10 to the negative 30, and that's in kilograms per mole because we're working with kilograms, not grams. And then we have the velocity, which is going to be how fast the feed is coming in, and that's going to be 5 meters per second. Then we have our liquid flow rate, our liquid feed rate, which is L, and that's going to be 0.5, and that's in kilograms per meter squared second. So it's good to notice that this is on an area basis, so per area. And then we have the pressure, which is just atmospheric pressure, which is going to be 101,325 pascals. And then the height of our cooling tower is going to be 20 meters. And then we are also converting our temperature of the water and air feed from Celsius to Kelvin by adding 273.15 to both the temperatures that were given to us in Celsius. What we also need to add here is that eventually we're going to graph these differential equations based on their position in the cooling tower. So we're going to have to make a z-plot based on those where z is the distance from the top of the tower, which we name z0, to the bottom of the tower, and which is 20 meters. So we're going to create a z-plot, and we're going to use linspace as we have in the past to create plots or points on this plot, equally spaced points on this line, so that we can graph at each meter. And so to graph at each meter, we know it's 20 meters in height. So we're going to go from 0 to our height. So if we ever change the height, it would this would change with it. which is nice. So we're going to start 0, go to our height, and we want 21 space points. 20 points might seem more intuitive, but if you do that, it will actually divide. It'll divide and give you 19 spaced, equally spaced, or it'll give you from 0 to 20, but it'll do 19 points instead of 20. So we want 21 points, and that will give us because we have to include 0. So if you're going from 1 to height, you could do 20, but since we want to start at 0, we need 21 space points to include 0. So we're every point from 0 to 20 will have a single meter point in which we can graph at. So 0, 1, 2, 3, etc. So now moving on to what else we need. We also need the mole fraction of air in the feed coming in. So mole fraction of air in the feed coming in, and we know that is just going to be equal to, in this case, what helps us is that we know that the the humidity is 50%. So we can just take 0.5 times the pressure, and this is where the Anton equation comes in, times the saturation pressure at a given temperature, and that temperature is going to be the temperature of the air coming in, the TA feed, and then we needed to divide that by P, or the total pressure. We also need to know the gas flow rate, or the flow rate of just the air, whereas in the parts in the past we have done the flow rate of everything, the entire feed. We just want the flow rate of the air now. So the gas flow rate of the air is equal to the total pressure times, and then we're going to also need the, this is where the molecular weight of the air comes into play, and that is equal to our molecular weight of air, those two times, and then we're going to divide the universal gas constant times the temperature of the air coming in, or TA feed, and then we're going to multiply that by the velocity at which it's coming in, which we were also given earlier. And since we're using initial value problem, we're going to go ahead and remember that initial value problem, solve IVP, takes initial guesses, and so we need to, here we need to give those initial guesses, and those initial guesses are going to be for the mole fraction of water coming out of the feed, as well as the temperature of the gas coming out. So we're going to go ahead and say that the mole fraction of water coming out, underscore, and then this is a guess, so we're going to call it a guess. And we're just going to say that, let's say the mole fraction of water coming into the, or mole fraction of water in the air coming into the feed is equal to, or we'll just take that as our baseline, and we'll just multiply by something like 1.1 to give us a guess. That's not going to be too far away from what it initially was coming in. And then we're also going to, like I said, the temperature of the gas coming out needs a guess as well. That's going to be equal to, let's just start as a baseline again, start with what we know, which is the temperature of the air coming in, and then we'll add, say, something that's not too big, not too small. Let's just say 5 Kelvin. We'll add 5 Kelvin to that to give us a guess that's going to be around that. And then we're also going to be using Sol as a variable, so we don't want to think it's the code think that it's a function, so, or any other term. So let's go ahead and set it equal to none, and none. Yep. Okay. So shift enter. Okay. So everything worked out there. So now we're going to go ahead and start defining the functions that we're going to use to solve our differential equations, as well as inputting the differential equations themselves. So what we want to do eventually is use IVP and root. So we're going to need functions for those uses of root and solve IVP. They require functions. So we're going to start by defining a function. We're going to say dy, which is mole fraction, the change in mole fraction of water. We also are interested in the change in the mole, or the temperature of the water, as well as the change in the temperature of the gas, with respect to z, as well as independent, or the variable v, where we'll store those. And let's go ahead and say that mole fraction of water, and then we need to say what those are. So we'll go ahead and say that the mole fraction of water is the first element in that v answer, or that v variable, and then same for TW and TG, or the temperature of the water and temperature of the gas, set it equal to, and remember that Python index is starting with 0. So now that we have those variables put into the or those changes being put into the v variable, we can go ahead and start by defining our functions now, which we can go ahead and start with the some equations, and then we'll go into some equations that we need to solve in order to use the for the differential equations to have the correct information on which variables they have still undefined. So we're going to start with the gas flow rate of the water, and we're going to say that is equal to the mole fraction of the water times, or not times, divided by 1 minus the mole fraction of water, multiplied by the gas flow rate of the air, multiplied by the molecular weight of the water over the molecular weight of the air, which gives us that fraction. And that gives us the gas flow rate of the water vapor. And then we also need the total gas flow. So the total gas flow is something new, but it's relatively simple. It's just the sum of the gas flow rate of the water plus the gas flow rate of the air. And then we're also going to need the average molecular weight, which is, again, these are all some variables that we're going to need to define in order for our differential equations to work. The average molecular weight is equal to the gas flow rate of the air plus the gas flow rate of the water. The gas flow rate of the air plus the gas flow rate of the water over the gas flow rate of the air. Gas flow rate of the air plus the gas flow rate of the water over the gas flow rate of the air over the molecular weight of the air, plus, and then it's the gas flow rate of the water over the molecular weight of the water. Okay, and then we're also going to need the heat capacity of the gas. So we'll say Cg, or the heat capacity of the gas, and then we need the heat capacity of the air times the gas flow rate of the air plus the heat capacity of the water as a gas times the gas flow rate of the water. And that is all going to be divided by the gas flow rate of the air. We're also going to need to know what we called NW in the other problem, which is the molar flux of water. So we used NW to shorthand a larger equation. We're just going to re-put that back in there. So that was the mass transfer coefficient divided by the universal gas constant divided by the temperature of the gas, multiplied by the pressure of the saturation pressure, so whatever temperature, and we're going to use TW now because we have TW stored in V1, so it's going to be the saturation pressure of the water at that given temperature now. And again, PV is using that equation back up at the top. That is the Anton equation, finding the saturation pressure at any given temperature. In this case, we're using TW now, and then we need to subtract the mole fraction of water times the total pressure. And again, that is what we found in a different part of the problem, and we're just rewriting it here. So what else we need is the differential equations now. So now we're going to input dy, dtw, and dtg, which are up here at the top defining our functions, and we're essentially putting those in now. So start with dy, which is the change in the mole fraction of the water. And again, we found that already, and that is equal to the negative, and remember it's negative because it's going against the positive z direction, which we defined. So negative specific area times the average molecular weight divided by the total gas flow times the molecular weight of water. And then we also need to know the dTW, so moving on to the change in water, the temperature of the water. The change in temperature of the water is the specific area over the liquid flow rate, and then we need to divide by the specific heat of the water as a liquid, or not specific heat, I keep calling it the heat capacity of the water as a liquid, and then we also need to multiply by the heat heat transfer coefficient times that heat flux, or the difference in temperatures. In this case, it's between the gas and the liquid, gas and the water. And then we need to also subtract the enthalpy of vaporization times that NW, which we just defined up closer. Again, like I said, these differential equations wouldn't work if you didn't define these functions up here above beforehand. And then finally, we need to figure out dTg, which is the change in temperature of the gas, and that's equal to the specific area times the heat transfer coefficient divided by the total flow rate of the air and gas, divided by the heat capacity of the gas, times that change in temperature again, or the difference in temperature between the gas and the water. Yeah. Okay, so, and now it's a function, so we want to return, and we want to return those values. We want it to return dy, dTw, and dTg. So when we return those functions, we need numbers at which they're going to converge to, or they're going to stop at. And right now in these functions, within this defined function, we don't have anything that these mole fraction of water, temperature of water, or the temperature of the gas are going to stop at. So we need to put this function within another function that's going to tell it when to stop or what to converge to. So we can go ahead and indent everything else, because we're going to start a new function, and we're going to define that function. Again, we need something that it's going to converge to. And then we're going to say that it's going to converge to, we'll just say the feed of the air is going to converge to, and then we're looking for the temperatures, the temperature of the gas, temperature of the water, as well as the mole fraction, and we're going to say that that is going to be, this just needs to be a second variable, so we'll call it V2. And we're going to say that the mole fraction of the water, the exit, and the temperature of the exit, temperature of the gas at the exit, are equal to that V. Again, just like we did with the y, tw, tg in the first function, we're going to do the same thing and put those functions into the variable v. So we're going to say that the y exit, or the mole fraction at the exit, is equal to the first element, and that the temperature of the gas, the exit, is going to be equal to the second element in that. Okay, so now that we have that, we're going to go ahead and use our, let's go ahead and shift enter to see. Okay, so that there are no errors in there, which is good. Hopefully there's no errors in by typing it out in the formulas, but if there is, we're going to find out very soon. So now we're moving on to the solve IVP problem. And just a couple notes before we start IVP. I noticed a couple issues that I had with my code that I forgot to do, and that this is V2. It was V, now it's V2 to correspond with this V right here. That's just a little mistake I made. And then also writing down the formula for the first differential equation, the change in mole fraction of water. I had an M here. It should be an N for the molar flux of water, not molecular weight. That would have been a totally different thing. Alright, but we can get started solving the IVP problem now. So for this equation right here, we can solve, we want to set that solution variable that we had frozen to none, so that we can now use it. We're going to hit sol is equal to, and then we're going to say it's that solve IVP, and solve IVP as a function. We can look, or as a package needs arguments. So the first argument it needs is a function. So we want to solve the initial value problem for the differential equations we just had, and then return those differential equations as solutions, or solutions, so that we want to return the solutions to the differential equations as an IVP, and then we're going to use the root solver to converge those to the function that we made above. So we want to start by doing the function that we just made, which is dy TWTG, that function. So that is the function we are using the IVP on. We need a time span, or what is happening over. In this case, it's going to be the distance, so it's going to be 0 to our height. And then we need y0, which are the initial values, and the initial values are for the mole fraction are going to be the mole fraction at the exit, the temperature of the gas at the exit, and then for water it's going to be temperature of the water at the inlet feed. So for gas, it's going to be our function, not guess, but the exit, temperature, water, feed. And then for the gas, it's going to be the temperature of the gas at the exit. Okay, so now that we have that, we don't really care about what method we're using. We're going to go right ahead to the set dense output equal to true. And then we want to solve this equation at every value along that z plot that has the linearly spaced positions from 0 meters to 20 meters, the height of our cooling tower. So we want to make sure that those values are solved at every value along that z plot. And then we want to return some of these values, and we want to return the solution to our first element, but we want to return the last element in that array. So to do that, we're going to say solution of our first element, but we want to return the last value, we want to return that last value from that array, and we want to subtract that last value from the mole fraction of water in the air to start with in the feed. And we want to do the same thing for the gas, so that the gas is our second element, or our third element, but second because remember Python index is starting with 0, and then we want again that last value, so -1. And then we want to subtract that one from the initial temperature of the gas, or in this case air, feed. So shift enter that. And then now we can go on to, like I said, we're going to use the root solver to find out where that solution is going to converge to. And then again, let's look at the arguments for root. We need a function, and the function that we're going to be converging to is going to be the converge function that we made up above. So that is our function. Now we need x0, which are our initial guesses that we had before. So these are where the initial guesses come in for the mole fraction of water and the temperature of the gas. So we have y out guess and the temperature of the gas out guess. Yep. So we have our two guesses, and if we run the root solver, it should converge. Y out exit not defined. Or am I using y out exit? It's not y out exit, it's just y exit. Okay, hopefully this solves it. Oh, now we got a big problem. Okay, what are we missing here? Maybe it's mixing. So something's wrong with the method, so maybe it's because we don't, I believe it's because we don't have parentheses around here telling it that that's the initial value, not a method. Okay. There we go. Okay. Yeah, so it was a problem with the method. It was thinking that these were method. I was thinking that that was a different argument and not the initial values. Okay, so the solution converged, which is good, and then it gives us our answer in this array right here. So what we're going to do now is we're going to move on to graphing it, but before we do, we have to remember that sol here is within a function, so in order to get sol to be used, so let's go ahead and see if sol works. Shift enter. The solution is not going to return anything, it's not going to give us anything because it's within a function, so we have to go above here and globalize the sol variable so that we can access it from wherever we want to outside of the function within a function. So now that we have globalized SOL, the solution to those the IVP and the IVP as well as the convergence solution from the root solver, we can go ahead and graph these solutions with the z-plot linearly spaced values from z-plot as the x value for our graphs, and the y value will be the solutions, the first, second, and third elements to the array of the solution function. So as the y-axis in our graph. So let's go ahead and make, and we're going to make subplots, and in the subplot we want rows equal to 3, and we want columns equal to 1. 3 rows, 1 row for each variable, and they're all going to be in the same column. This time don't need more than 1 column, and then we're going to start by adding traces and fig.add, and this not traces, but we're going to add scatter plot. The scatter plot, like I said, needs a x-axis, and that x-axis is going to be the z, not capital Z's plot, which is those, like I said, linearly spaced points from 0 to 20, which 20 being the bottom of the cooling tower and 0 being the top. And then the y-axis is going to be equal to the solution, the first element, because we're doing the mole fraction of water first, the first element, and we want it to graph every single value in that array. So comma colon is the function that does that. And then we want to name it. And like I said, this is the mole fraction of water, so let's call it YW. And then we're going to set the row, we're going to set this to the first row, first column. See if that graphs. Oh, it's not z-plots, it's just z-plot. Okay, so that gives us the first plot. So we're going to go ahead and copy and paste this and do this with the other ones. Okay, so z-plot stays the same. However, the solution, we want the first and, well, the second and third element, but the 1 and 2 because the index is from 0. And then we'll change this one to, I believe, we want the temperature of the water. Yeah, temperature of the water second, temperature of the gas last. So rename those, change this to the second row, change this to the third row. I think that should be it. Should enter, get our graphs. Okay, so these are our graphs. They look kind of smushed now. Let's go ahead and change the width and height just a little bit so that it looks a little bit better. So we're going to fig, and we're going to update our figures. We want to update the layout because that's how you update the width and height of the graph. So we're going to set the width equal to, let's try 600, and the height, I've actually already graphed these, so the height, these width and heights look pretty good. So we're gonna go with these 600, 900. Okay, so can I zoom out now? Let's try and zoom out and get, holy cow, it's really zoomed out. Okay, well, I was hoping you could see them all at the same time, but we'll just go through all of them. So starting with the mole fraction of water, these are our graphs, so let's see if they make sense logically. So starting with the mole fraction of water, so if you think about the original problem, the mole fraction of water should be the greatest at the top, and as it goes towards the air inlet, it should decrease, and that's what we say here. 0 is at the top of the cooling tower, and then that is where the mole fraction of water in the air is the highest. And as it gets closer and closer to the source of that air, the inlet feed, it gets lower and lower, which makes sense. So moving on to the temperature of the water. At the top, the temperature of water is the highest, and then it decreases as it goes down, which I hope is the case considering this is a cooling tower and the whole objective is to cool down the water. But yes, as the water starts here, it's around 343 degrees Kelvin, and as it gets down to the bottom, it's around just under 300 degrees Kelvin. So yes, the water is decreasing in temperature because as it is going through the air because of evaporation reasons, and that is why the water is decreasing temperature. Then the air is temperature of the gas of the air, and at the inlet feed is actually here. So the temperature of the gas is the lowest at its inlet feed, and then as the air flows up the cooling tower, it gets hotter and hotter. which makes sense because the heat from if the water is cooling down, the air is heating up because of the transfer of heat from the water to the air. So these graphs all make sense, and this is where we end exam 3.